Okay, so on Tuesday, we were finishing up, we were talking about ionic compounds. Ionic compounds are the electrostatic attraction between a cation, a metal, and an anion, whether that is a non-metal or a polyatomic ion. The cation results from the loss of one or more electrons, and if it is an anion of an element, that results from the gain of one or more electrons. The formula unit is the smallest unit. It's kind of like it is an empirical formula. But for an ionic compound, the formula unit and the empirical formula are going to be the exact same. It's going to be the smallest unit where you have this electrostatic attraction. But you do have to realize that in an ionic compound, that's just a small piece of the overall, because once this ionic compound forms, we make lattices. Now, the ionic compound, again, is the result of a metal losing its electron or electrons. Or you could say it's the result of transferring that electron or electrons to a non-metal. The non-metal gains the electron or electron. And the result is, with the metal losing an electron, it has an overall positive charge because there's more protons now than there are electrons in the atom of the element. And the non-metal becomes negatively charged because there are more electrons than protons in the atom of the element. Once you make your cation and your anion, they are going to be electrostatically attracted or magnetically attracted to one another. Now, the way we write the Lewis structure for an ionic compound is we place the ion in the Lewis structure of the ion in brackets with the charge outside. So since sodium lost its electron, you will notice there are no dots. There are no valence electrons around this sodium atom. And we place the sodium atom in brackets with the charge outside. Now, chlorine gained electrons so that it has 8 valence electrons. So we illustrate those 8 valence electrons as dots. And because this is an ion, we place the Lewis structure in brackets with the charge outside. That electrostatic attraction of the sodium, which is represented with a purple, and the chlorine, which is represented with a green. That is one formula unit. One sodium and one chlorine is the formula unit. It is also the empirical formula. Now, when this sodium chloride, because it's just an electrostatic attraction, just a magnetic attraction, what we wind up forming is this nice, beautiful lattice where we have positive charge connected to a negative charge. That negative charge is connected to other positive charges. And so we wind up forming this lattice. Let's look at another example. Let's look at sodium oxide. Sodium oxide has the formula of Na2O. Each sodium atom has 1 valence electron. The oxygen atom has 6 valence electrons. The sodium transfers its valence electron to the oxygen. The second sodium transfers its valence electron to the oxygen. So what we wind up with is 2 sodium atoms that have no valence electrons, and therefore we place that in brackets with the charge outside. And you wind up with oxygen. The oxygen now has 8 valence electrons. You place the 8 valence electrons as dots around the electron symbol, and then you place the ion in brackets with the charge outside. So the formula the Lewis structure for sodium oxide would be 2 sodium ions and an oxide ion. Notice there is no line between these two. There is no line because this is an ionic compound. And I'm saying that for those individuals that have discussed Lewis structures in their past. Because if you've discussed Lewis structures in your past, you typically think of a bond occurring between the atoms. That is true for a molecular formula. It is not true for an ionic compound. There is no line. There is no bond. It's because this is simply an electrostatic attraction between the cation and the anion. Here is a diagram of the beautiful lattice structure that sodium oxide forms. Again, the sodium is represented with a purple circle, and the oxygens are represented with a red circle. And you start to see that these oxygens are connected to 4 sodiums just because of how they arrange. But you get this nice lattice energy again. The formula unit is Na2O. That is its empirical formula. That is its molecular, that is its formula, period. Any questions about sodium oxide? So we're going to do a couple of examples. We're going to use the Lewis model to predict the formula unit of a compound between calcium and chlorine, and the formula unit between a compound of magnesium and nitrogen. So let's begin with calcium and chlorine. Calcium is in group 2, so how many valence electrons does it have? 2. Chlorine is in group 17. The last digit is a 7, so it has 7 valence electrons. Now, the metal is going to transfer its valence electrons. This calcium can only transfer 1 electron to the chlorine. Therefore, you have to have a second chlorine for the second electron to be transferred. Because the calcium, we know, forms a +2 charge because it's going to lose 2 valence electrons. But each chlorine can only accept 1 of those valence electrons. So what we wind up forming is a calcium ion that's a 2+ charge due to the loss of its 2 electrons. And we wind up forming 2 chlorine ions that have 8 valence electrons. Each chlorine ion has a -1 charge. So the Lewis structure for calcium chloride would be calcium ion and 2 chloride ions. Now, you may actually see this written differently depending upon the... You could write this another way. You could also write it as, okay, I have a chloride attached to a calcium, and that calcium is also attached to another chloride. Both of these are acceptable versions because they mean the exact same thing. You have a calcium ion attached to 2 chloride ions. Things to note. Number one, the metal loses all of its valence electrons for the main group metals. Second thing to note is that the non-metal gains electrons to get an octet, or 8 valence electrons. Why does it do this? Well, again, if we were to look at the calcium ion, we would see that it now has an electron configuration of argon. If we were to look at the chloride ion, we now see that it has an electron configuration of argon. So by the metal losing its valence electron, it obtains a noble gas configuration. By the non-metal gaining 1 valence electron, they obtain a noble gas configuration. Let's look at the next example, which was magnesium and nitrogen. Magnesium is in group 2, so it has 2 valence electrons. Nitrogen is in group 15, the last digit is a 5, so it has 5 valence electrons. Whoops, I drew one. Well, I'll just go ahead and make that line. The magnesium is going to donate its electrons to the nitrogen and it fills in, but is the nitrogen full? No. So we're going to have another magnesium so that that nitrogen can be full. But now is the magnesiums completely devoid? No, we have a magnesium that still has a valence electron, so we're going to react it with another nitrogen. But is that nitrogen completely full? No, so we're going to react it with another magnesium. Are all the magnesiums devoid of their valence electrons and all the nitrogens? Do all the nitrogens have 8 valence electrons? Yes. Therefore, for magnesium, it takes 3 magnesium ions and it takes 2 nitrogen anions in order for all of the magnesiums to be devoid of their valence electron and all of the nitrogens to have an octet. Question. You won't have to do this on this test, but you will have a Lewis structure of an ionic compound on the next exam. So the development of the Lewis structures will be on the next exam. Exam 3. Okay. Since there are no questions about what I just did, Then let's move to the next. One, which we're going to discuss the lattice energies. Folks, energy is the real reason behind the formation of compounds. We keep saying, okay, the metal is going to lose its valence electron so that it obtains a noble gas configuration. The nonmetal is going to gain valence electrons so that it obtains an octet, which is a noble gas configuration. That method of thinking is very useful. But if we want to get down to the nuts and bolts about why ionic compounds form, we have to look at the energy. Now, if you'll recall, ionization energy describes the energy associated with the formation of a cation. So with our magnesium cation that we just made in the last molecule, we would have the first ionization energy of each magnesium and the second ionization energy of each magnesium. In order to create magnesium 2+ cation, you got to add a lot of energy into the molecule to make it happen. Now, if you look back at electron affinity describes the energy associated with making an anion. And if you look at the electron affinity for nitrogen, it was greater than 0, meaning we got to add energy in order to make the nitride ion. So magnesium ion, making a magnesium ion and making of the nitride ion does not explain why magnesium nitride forms. It doesn't explain it. The only thing that can explain why an ionic compound will form is the lattice energy. Because when that cation and that anion are attracted to one another, they generate energy. And they generate more energy than was required to make the cation and anion. So that the overall process of making magnesium nitride is favorable. So again, making the cation, that's not favorable. Making the anion, that's not favorable. But when that cation and anion comes together, the process is overall favorable because it generates a lot of energy. That is called the lattice energy. Now, when we get to chapter 9, we'll actually look at how to calculate the lattice energy. We're not going to do that right now. So in other words, we're coming back to this later on in the semester. But instead, what we're going to do is we're going to look at the trends in lattice energy. So again, the lattice structure is very organized. There are not distinct molecules. Instead, it's rather a super large chain of ions. The formation of those ions is not favorable, but when they come together, to make the ionic compound when they are attracted to one another through the electrostatic attraction. That is overall favorable. And it is what drives the formation of the ionic compound. Now, what we're going to do is we're going to inspect some trends. And from that, we are going to deduce key points about lattice energy. Again, it's the energy attracted by the attraction between the cations and the anions. So let's look at this graph. If I can get it to stay where I want it. When we combine lithium ion with fluoride ion, the lattice energy gives off roughly 1,050 kilojoules. When you combine lithium ion with chloride ion, the lattice energy gives off around 850 kilojoules. When you combine lithium ion with bromide ion, that's now down to about 790 kilojoules. When you have lithium combining with iodine, that is now around 750 kilojoules. Using lithium only, what can you say? This is going to be an interaction. If we're talking about lithium only and its behavior, what can you say?
The closer that your elements move towards the number less, the less energy they give off.
Well,
The bigger the atom is, the bigger that the atom is, the less energy that it's going to give off.
exactly. The bigger the anion, the less energy. The less the lattice energy. Or if we're talking lithium compared to potassium, you will notice the same thing. Lithium with fluorine gave off roughly 1,050, whereas potassium with fluorine is just barely over 800. The bigger the ion, the less energy. The lower the lattice energy. The bigger the ion, the lower the lattice energy. That is one important fact. I want you to take a few moments and I want you to really study this. And what I would be doing is I would be looking at lithium with fluorine and lithium with oxygen. I would compare all that with calcium and fluorine and calcium and oxygen, and then aluminum and fluorine and aluminum and oxygen. I would look at those three and try to find some sort of trend buried in there. Anyone have folks, it's okay if you get it wrong at this point. Anyone have a guess?
Is it related to how reactive it is? Like, cause if you look relative to where they are on the periodic table, the ones farther to the left, away from the noble gases they have like less energy given off than like, say, aluminum, which is farther over towards the noble gases.
You're on the right track. Not quite there.
The bigger the anion, the bigger the energy. Right?
The bigger the anion, what do you mean by bigger the anion? Because technically,
Nothing.
chlorine, bromine, iodine's bigger, but if I look at fluorine and oxygen, yeah, oxygen's bigger. Oxygen's bigger, but how does that compare to calcium and aluminum? Because aluminum's smaller.
Yes.
Aluminum needs more atoms to fill up with oxygen. Glass. Need multiple aluminum, multiple.
Very close. Doesn't have to do with iron radius this time.
Charge.
It's the charge. The bigger the charge, folks. Ions don't like to exist. They like to exist, but only if they're part of a compound. And remember, it takes so much energy to make a aluminum ion that it's gonna have to give off a lot of energy when it comes into that lattice. So everyone was hinting around at the right thing, but it comes down to the charge. The larger the charge, fluorine compared to oxygen, the larger the charge, the bigger it is. If you compare lithium and aluminum with fluorine, or the larger the charge, the more dynamic the lattice energy. So what we can say is there are two factors. Well, come on. I didn't mean for you to do that. The most important factor. This is in order of importance. The most important factor is the larger the magnitude of the charge, the larger the numerical value of the charge, the greater the lattice energy. And the second most important is the smaller the ion, the greater the lattice energy. When I look at a series of lattice energies, what I'm going to do is I'm going to first sort it by the magnitude of charges. And then if they have like charges, then I'm going to sort it by the size of the ion. So again, I'm going to sort it by the charges. And then if they have like charges, then I'll sort it by the size of the ion. Let's look at an example. This is similar to what you're going to encounter on the exam. Sort these in order of increasing lattice energy. So I'm going to be going from the lowest lattice energy to the highest lattice energy. So step number 1, I said I'm going to figure out the charges. Lithium has a +1 charge because it's in group 1. Iodine has a -1 charge because it's in group 17. Calcium has a +2 charge because it is in group 2. Sulfide has a -2 charge because it's in group 16. Magnesium has a +2 charge because it's in group 2. Oxygen has a -2 charge because it's in group 16. Sodium has a +1 charge because it's in group 1. Iodine has a -1 charge because it's in group 17. Lithium has a +1 charge because it's in group 1. Chloride has a -1 charge because it's in group 17. What that does is it allows me to say, okay, I know that calcium and sulfur and magnesium and oxygen are going to have the highest. And I know that lithium iodide, sodium iodide, and lithium chloride are going to have the smallest. The lowest lattice energy. Now I need to sort these because I've sorted them by charges. Now I'm going to sort them by size. If I look at, so what I see next is, okay, period 2, period 5, period 3, period 5, period 2, period 3. Over here, it is period 4. Yeah. And period 3. And magnesium is in period 3 and oxygen's in period 2. I did that because remember, as you go down a group, the size increases, and that's the most predominant piece because of shielding. So I sorted it by period first with respect to atomic size. And in doing so, what I can see is I would expect sodium iodide to have the lowest because it's a +1, -1, and it's also the elements in the largest, the largest ions. I would expect out of lithium iodide and lithium chloride that lithium iodide would be next because of that iodine being a larger ion than the chloride. So I'd expect lithium chloride to come in third. Now, calcium sulfide and magnesium oxide. Because calcium is in a larger, and the sulfur are in larger, larger periods, that means they're going to be larger atoms or ions, and therefore they're going to have a lower ionization energy. So calcium sulfide would go next, and then we would have magnesium oxide as last. So again, I sorted by charge. And then I sorted by size. And remember, there's 2 factors that impact size. Factor 1, which is the most predominant, is shielding as you go down a group. Or, as you increase in periods, basically. The second most predominant factor would be that the size decreases across a period. I would have had to use that if I were talking about elements in the same period. Question? So that is lattice energy. Again, we'll learn to calculate lattice energy in chapter 9. But right now, you just need to understand the trend, and the trend is based off of the charge and then the size. Questions? Okay. So basically, if you look at the last two in-class presentations, PowerPoints, it's all been about, for the most part, ionic compounds. Now we're going to talk about how, and what we've been doing at this point is simply, number one, determining the Lewis symbol for the element. From there, we illustrated the transfer of electrons from the metal to form a cation and the gain of electrons by the nonmetal to form an anion. The reason we gave was because of the octet rule, or the desire to become a noble gas configuration for the main group elements. Where the metals lost all of their valence electrons to obtain that noble gas configuration. And the non-metals gained enough electrons to obtain a noble gas configuration. And we were able to look at those Lewis symbols and go, okay, magnesium's already lost both of its electrons, but nitrogen's not full. So we had to add another magnesium. Okay, now we filled up the magnesium or the nitrogen, but the magnesium still has one valence electron left. So we added another nitrogen. And we did this until all of the metals, or until the metals had completely lost their valence electrons and the non-metals had gained an octet. From that, we were able to discern what the formula would be. That's a hard way to do it. I mean, it's important to understand the Lewis structure, but it's a hard way to do it. The second thing is about the fact that the driving force is the lattice energy. The driving force behind the formation of an ionic compound is the lattice energy. And we talked about the lattice energy. What we're going to do now is we're going to develop the formula of ionic compounds in a much simpler fashion. And we're going to start to learn to name ionic compounds. The formulas of the ionic compounds can be determined from the charges. We will look at these charges and we will combine metal cations and non-metal anions until we are able to obtain a charge neutral compound. Because all formulas of ionic compounds should be charge neutral. Let's look at this in process. We're going to do it a couple of different ways, but the first way is just going to illustrate this. So what is potassium's charge? +1. And how did you know that? Because it's in group 1. It's one of the ones I asked you to memorize. Fluorine, as an anion, would have what charge? -1. Why? Because it's in group 17. So we have a +1, -1. The question is, does that equal 0? Yes. So in other words, potassium combines with fluorine in a 1-to-1 ratio. That 1-to-1 ratio is shown or is indicated by simply the symbols because we don't show ones. Let's look at the next example. Magnesium and fluorine. Magnesium's charge is what? +2 because it's in group 2. Fluorine, we've already said, is a -1. Does +2 -1 equal 0? No. So this does not occur in a 1-to-1 ratio. What is in the lowest supply right now? The positive or the negative? Negative. So let's add another fluorine. And now we have a +2 -2. Does that equal 0? Yes. So magnesium fluoride occurs in a 1-to-2 ratio. Now again, this is tedious. There is a simpler way. The simple way is we are going to cross, drop, and simplify. We are going to cross the magnitude and drop that magnitude on the opposing atom. And then if the subscripts can be simplified, we should do so. So aluminum, what is the charge of aluminum? 3+. Why? Because I told you aluminum, gallium, and indium are all 3+. That's the only charge those elements form. Oxygen is what? It's 2-. Why? Because it's in group 16. We are going to take the magnitude and we are going to cross and drop it on the opposing atom. We're going to take the magnitude and we're going to cross and drop it on the opposing atom. So on aluminum, we're going to drop a 2. On our oxygen, we're going to drop a 3. And therefore the formula, and then we're going to simplify. But in this case, the only number that these two subscripts are divisible by is 1. Therefore, it is in its simplest notation. So the formula for aluminum and oxygen is Al2O3.
it would mean if we're trying to do the Lewis structure that we would have 3 aluminum 3 pluses, 2 aluminum 3 pluses and 3 O2 minuses. Let's look at the next example. We have Fe2 plus. Why have I told you the charge on the iron? Because it can have different charges. So I'm gonna have to specify somehow what that charge is. And you're gonna see that throughout the process. And oxygen, we said was a 2 minus because it's in group 16. Plus, so we're gonna cross and drop the magnitudes. So on our iron, we would drop a 2. On our oxygen, we would drop a 2. These are both divisible by 2. Therefore, we're going to do so. And so the formula for a compound of Fe2 plus and oxygen is simply FeO. The Lewis structure would be iron 2 plus O 2 minus. Questions? I do have a question that nobody's asking. If I look at the electron configuration for iron 2 plus, it is argon 4s2 3d6. Why aren't the d electrons shown?
It's not the outermost shell. It's not the outermost shell, it's not a valence electron. And remember, these only represent valence electrons.
Okay. Silver sulfate. What is the formula for silver? It is Ag plus. Remember that forms a stair step starting with Ag. And the number of elements in the stair step represents the charge. So silver has a +1 charge, whereas zinc and cadmium are both +2 because there's 2 elements in the step. Aluminum, gallium, and indium are all +3 because there's 3 elements in the step. So silver is a +1. We're going to see how many people have looked at their polyatomics. What is sulfate? First of all, how do I know it's a polyatomic ion? Hmm? Yes. Polyatomic ions, the majority, there's 3 exceptions. But all the rest of them end in either ATE or ITE. Whereas elements end in IDE. That's how I knew it was a polyatomic, is because of what it ended in. It ends in ATE, therefore it has to be a polyatomic. Sulfate is SO4 2 minus. Now, we're going to do the same thing. We're going to take the numerical value, and since 1 isn't shown here, that means it's a 1. We're going to cross and drop it on the opposing ion. So on silver, we're going to add a 2. On sulfate, it's only going to be a 1. We cannot simplify this formula. So the formula for a compound of silver and sulfate is going to be Ag2SO4. Yes. Okay. Let me do a separate example. How's that? Let's do calcium and phosphate. So calcium 2 plus and phosphate 3 minus. We're going to cross and drop. So on our calcium, we're dropping a 3. Now, to your question, if you drop a number greater than 1 on a polyatomic, the polyatomic goes in parentheses with the number you drop on the outside of the parentheses. Now, let me explain why. When we drop this 2, we're saying, hey, I've got 2 phosphate units. The unit is PO4. So this number is saying I have 2 of those phosphate units. And that's how we do it if we have to drop a number greater than 1. Yes.
Will you always give us the charges of the polyatomic ions?
Oh, no. You're going to have to memorize those for the next time. I'll tell you, I will give you a shortened list that you have to know for test purposes, but you're going to have to know your polyatomics and tests. Now, folks, these polyatomics is in this big packet that I gave out on Thursday. They start on the second, really they start on the second page. And there's a huge list. If you watch the video on ions, the flipped classroom video on ions, I tell you how to memorize these. But, like I said, I'll give you a short list and you can memorize them. So. Cobalt and hydroxide. Again, why did I give you the charge on the cobalt? Because there's more than one possibility. Cobalt can be a +2 or it can be a +4.
Now, hydroxide, there are only 3 polyatomics that end in IDE. This one is OH minus, that is hydroxide. Yes, you need to know this. The second one is O2 2 minus. This is the peroxide ion. And the last one is CN minus, which is cyanide. These are the only polyatomics that end in IDE. All other IDEs means it's an anion of an element. Again, these are the only polyatomics that end in IDE. All other IDE means that it's an anion of an element. So it's an anion of a nonmetal. So this is cobalt hydroxide. We're going to take the number, we're going to cross and drop it onto the opposing atom. Because hydroxide is just a negative, that means it's a -1. So we're going to drop a 1 onto our cobalt. Again, because we are dropping a value greater than 1 on a polyatomic, we're going to place that polyatomic in parentheses with that value as a subscript. That literally says I have 2 hydroxide units for every 1 cobalt unit. Questions? Naming ionic compounds. So in this process, I gave you metals, just their name: aluminum, silver, calcium, and I expected you to know their charges. The reason I expected you to know those charges is because those elements always have the same charge. These are metals that form only one type of ion. When you have a metal that forms only one type of ion, you name the cation, and then you name the anion. And if it's an anion of an element, it gets the ending IDE. If it's a polyatomic ion, it gets its name. But again, you name the metal and you name the anion. If it's an anion of an element, it gets IDE. If it's a polyatomic ion, it gets its name. Now, we also encountered cobalt 2+, iron 2+. And in those particular examples, I gave you the charge on the metal. The reason I had to give you the charge on the metal is because those metals can make more than one charge. So when a metal forms more than one type of ion, we're going to have to not only state the name of the cation, but I'm going to have to tell you what that charge is. Just like in my examples, I had to tell you it was Fe2+. I had to tell you it was CO2+. I have to tell you what that charge is. And the way we do so is we use Roman numerals to indicate what the charge is on the cation. And then, just like with our other compound, we name the anion. If it's an anion of an element, it's going to get the ending IDE. If it's a polyatomic ion, it's going to get its name. So what are these Roman numerals? Well, they're the same Roman numerals that you see. If you got one, if it's a +1, or then it's going to be the Roman numeral for 1. If it's a +2, it's going to be the Roman numeral for 2. If it's a +3, it's going to be the Roman numeral for 3. If it's a +4, that's going to be the Roman numeral for 4. 5, Roman numeral. 6, whoops, and 7. Now, we don't have any Roman numerals greater than 7 that we're going to worry about. In fact, there's very few elements that actually can form a 7. Manganese is one of them. But there's very few elements that form a +7. You will encounter 1, 2, and 3 quite a bit, and even 4 quite a bit. But 5, 6, and 7. Anybody want to tell me why they think 5, 6, and 7 may not occur very often? Think about what we've talked about. Think about what's coming up on the test. Huh? It takes a truckload of energy to get that many electrons pulled off of an atom. It isn't going to occur very often. So again, you got to know who's who. Group 1s +1, group 2s +2. You got to know this silver, cadmium, zinc, aluminum, gallium, and indium staircase. Those are the ones that I'm asking you to memorize of the cations. The rest of them, we're going to use a Roman numeral for. So these, there's no Roman numeral. For most of your for most of your transition metals, and larger metals, you're going to need a Roman numeral. Again, you got to know who you do and who you don't need a Roman numeral for. These are the ones you don't need the Roman numeral for that I have boxed in as dramatic as I can get. All other metals, you gotta have a Roman numeral. Questions? Next Thursday, we'll pick up with names and formulas of ionic compounds and move to names and formulas of molecular compounds. Come prepared with your sheet of ions and start, after the test, start learning those ions.